Thank you. So, buenos días a todos, bienvenidos a este Seminario Torroja. Hoy tenemos el placer de contar con Giga Casar, and he doesn't speak very good Spanish yet. We have to move into English. Sorry. So, Giga Casar, I have put a brief summary there. So, he is currently a senior postdoc at the University of Basel. He did his PhD at EPFL under the supervision of Professor Bowen, Professor Scribner, and also Professor Kuni Mohammed on the topic of atomistic modeling of CSH, bulk, and surface. So he has been afterwards moving around, okay, with a very prestigious mobility grant from Switzerland. He went first 1 year to Durham University and 1 year to Princeton University. And he has some other award I also have pointed out there also on teaching. So his main specialty, his main strength is on CSH modeling. And why is important then that? You know, calcium silicaluminate is calcium silicate, right? Is the hydrated is the most main component or main product in our cement, responsible of mechanical strength. So if we understand better that structure, we can understand better this strength, better the durability, better transport properties. So he is not only expert on the simulation, he's also becoming a great experimentalist. So he's producing now his own CSH, validating all these models, so that is very good. And obviously also he has written several papers, very relevant. Some of them I have put it, that has been published very recently, in physical chemistry, chemical physics. So I'm sure you will talk a little bit or a little bit about that. And just as a research areas, I put, yes, calcium silicate, hydrate, atomistic modeling, and material characterization. Please take advantage that he is here. If you want to discuss things afterwards, not only in the seminar, if you want to discuss specific topics, he can give you very good ideas, by the way. And anyway, it's a pleasure. He's talking about, the title of the presentation is Structure and Precipitation Pathways of Calcium Silicate Hydrates. So thanks again, Giga, for coming. Okay.
Introduction?
Oh, sorry.
Yeah,
so
it's okay.
You do it.
To do like this, I think. Okay, thanks for having me. So yes, I will talk about structure and precipitation pathways of calcium silicate hydrate. So it's kind of a mix of experimental and modeling. So there was a lot about me, so we can skip that. Yeah, so I mean, I guess we're all same passionate about cement and concrete, and we know that there are like two main challenges. One is reducing the 8% CO2 footprint of the concrete industry, which we're doing through using supplementary cementitious materials, but that impacts early strength. And then the other problem is the durability of concrete, which comes due to ions penetration into the concrete structure. So to tackle both problems, like I think we really need a really good fundamental understanding of CSH, so calcium silicate hydrate. And that's because CSH is the main hydration product. It makes up to 50–60% of hydrated cement paste. And we know now that its nucleation growth are the controlling steps of the hydration reaction, which is the SEM problem. And it forms the nanoporous network that controls ion transport, which is the durability problem. So the outline of my talk is, I'm going to show how we do the CSH in the lab, the setup, and then we get like two different morphologies depending on the solution conditions. But then I will really dive deep into the atomic level structure of the CSH nanofoil, talk about its solution-dependent surface structure, and then I'm going to try in a few slides to point out why it matters and how you can use it in actual cement paste to interpret phenomena. So we make synthetic CSH, so phase pure CSH, no Portland and nothing, just pure CSH. What we do is we follow the synthesis protocol developed by Professor Bowen at PTG at EPFL, which was first published in the Kumar paper, and then standardized by the Harris paper in CCR. So basically what you do, you have a reactor and you have 0.1 molar of sodium metasilicate solution, and you slowly titrate calcium nitrate solution in it. So if you don't titrate too fast, we're talking about 2 milliliters per minute, and you really control the temperature, 20 degrees Celsius, you have argon or nitrogen atmosphere so that you don't have carbonates in it, and you really mix very good, you're going to end up with a phase pure CSH. Okay, so no Portlandite, nothing. You filter it, you get the wet gel, which you see here, and then you can dry it and use it for characterizations like we do. The nice thing about this is that you don't need to wait a month to make CSH, but it takes 5 hours, so 6 hours. 1 hour to measure everything, cool down the system. You start the precipitation, it takes for 200 milliliters, 100 minutes, it's done. And then you mix for another 3 to 5 hours so that everything is nicely liberated, and you have your CSH. And by adjusting the pH, you control what calcium silicon ratio, mean chain length, and similar you have at the end. So higher pH generally means higher calcium silicon ratios. And I think the highest that was produced by Maya was a calcium silicon ratio 2.1 without Portlandite on the side. So we use this setup and we adjusted the pH, either way raise it a little bit by adding sodium hydroxide or lower it to go to lower pHs with nitric acid. And if we start with a pH of 13 in our sodium metasilicate solution, we get a foil morphology where the foils are more than 100 nanometers long with a calcium silicon ratio of 1.32. And they have, this is the blue XRD, they have the typical CSH reflections. I'll talk more about it later, a lot more about it later. And the globule forms if you have a pH 12 or like 12.4 and less, and globules are around 20 nanometers long. Ours has a calcium silicon ratio of 0.68. And by the XRD you see they don't really have any typical reflections. Also, the silicate speciation is different. So in CSH you usually have Q1s and Q2s, those are typical, where globules are more heavily ours on Q3 and Q2s and very rare Q1s. And by synchrotron PDFs we can see that while CSH foil still has some mid-range to long-range order here in this part, globules appear completely amorphous after 7 angstroms. So they seem morphologically and structurally completely different. And if you, there's a paper in Inorganic Chemistry from 2024 where they took amorphous calcium silicate, which you can just buy, it's a chemical, calcium silicate ratio of 0.3. It has a very similar XRD pattern, no peaks, very similar. The speciation shifts to Q4s, which is, I guess, because they don't have so much calcium, but at the end it just confirms to me that the globules are indeed a completely amorphous calcium silicate, probably not even hydrate, okay? But that's enough on the globules, because I have, as my friends say, an unhealthy obsession with a nanofoil, which is the morphology that we find in cement paste. So CSH in cement paste, as you know, we have the allied grains, and then on the allied grains you grow CSH, and you have the inner CSH or the denser product, high dense CSH, and the outer CSH, which is less dense. And there's like nice, you can in the literature you can find nice pictures of CSH growing on those C3S grains in foils and in needles, but even the needles appear to be actually nanofoils. So they're like kind of stacked nanofoils. So yeah, so to understand the atomic level structure of CSH, we first need to go to tobermorite, which is an in nature occurring mineral with a calcium silicon ratio of 0.83. It's kind of a clay. So you have those are the main layers, which are separated by interlayers, and they're stacked. And its characteristic for it is that you have this calcium oxide sheet, which is sandwiched by the silicate chains, okay? And the silicate chains are, we say, infinitive long because they're not defective, and they follow the Dreyer-Ketton structure. So basically, you have always a pairing silicate and then a bridging, okay? And those are Q2 silicates because each silicate is connected always to two other silicates. And then the interlayers are very well defined. So in the case of tobermorite 14, the interlayer space is 14 angstroms, and interlayer has 7 water molecules and 1 calcium. And because it's a crystalline material that you can grab with your hand, it has very defined reflections, okay? But then when we go to calcium silicate hydrate, CSH has a much higher calcium silicon ratio. Usually in cement paste, you can find it from like 1.4 to 2. Depending on the system, we can go to 2.1 nanofoil geometry. But the whole point why tobermorite is a model system of CSH is because you can fit the XRD pattern of CSH with the B11B subcell of tobermorite as defined by Bonacorsi. And the fit is like really remarkable. You fit all the reflections very nicely. So that's why it's the base. And the nanofoils by itself, experimental measurements say that they're between 1 and 6 nanometers thick. Depends on how you make them with the solution conditions, the precipitation conditions, the materials used. But rarely anybody reports them thicker than 6 nanometers. And this thickness corresponds to only 1 to 5 stacked main layers. So in our practice, like tobermorite is still a crystal material, so it's kind of defined by its bulk structure, but the nanofoil is very thin, so it doesn't really have a very defined bulk structure. And the surfaces seem to play a big role. So the nanofoil by itself, I like to take it apart into 3 parts. So you have either way the calcium silicate main layers, the interlayers, and the surface structure. And each of them has its own specific characteristics that I will explain. So as I said, in tobermorite, that's in nature occurring, in one which was found in nature, the silicate NMR. So you see that majority of silicates are indeed Q2. There's like some amount of Q1s, but basically it says, like I said, that the chains are infinite and they're always go dimer, dimer, bridging, dimer, dimer, bridging. So all the bridging silicates are present. But as it was done here in the Kumar paper from PTG, our lab, we see that as the calcium silicon ratio increases, so increases down, we have less and less Q2P and Q2B silicates, which means that as we increase the calcium silicon ratio, which corresponds to increase of the solution pH, we have more and more of those bridging sites actually missing, and that's the key defining feature of CSH. And in the same paper, they nicely showed with combination of NMR and quantum mechanics calculations that those sites are occupied by calcium atoms stabilized in it with hydrogen bonding, and this is a partial increase of the calcium silicon ratio that we see in the cementitious CSH in comparison to the tobermorite structure. So this kind of defines the nanofoil main layer structure. So we have the calcium oxide sheet, which seems the same as in tobermorite. We have the, I call it in-chain silicates. Oh, I did not mention, when you remove the bridging site, this one is not anymore connected to 2 silicates, so it's Q1. That's why in the NMR we have more and more Q1 species in comparison to Q2. So so the main layer seems like very structured in the calcium oxide sheet. It's just the missing bridging sites which are occupied with calcium in comparison to the tobermorite structure. But generally, as you can see, like here, the tobermorite XRD has those many reflections, but the CSA structure has only those 5 typical reflections. And it was like long time thought that it's due to structural defects, or I don't know, it's amorphous, but actually they showed, the Souza showed in his paper back 3 years ago, that this is actually a consequence due to the random stacking of those layers. So they had a completely crystalline Tauber-Morais structure, and they just twisted the layers, like a little bit tangled or reoriented, and then you start getting like the actual, you can model the XRD pattern that you experimentally see. So it seems that CSH main layers are completely very crystalline in the calcium oxide sheet, and the broadness of reflection only comes due to the random stacking and the thin morphology. Which kind of makes it interesting, because if you have different Tauber-Morais, and one special case of Tauber-Morais is where the silicate chains through the interlayer get interlinked, okay? So when the interlinking of those Q2 species occurs, the Q2 becomes a Q3, and they're sometimes experimentally seen. But if you have this broadness of CSH XRD reflection, and you kind of twist it and stuff, you don't have perfectly aligned layers, so a Q3 is technically impossible in the CSH structure, in the cementitious CSH structure, and they're only reserved for perfect crystalline Tauber-Morais. So prohibited by the random rotation of stack layers. So that kind of brings me to CSH nanofoil structural axioms, which are kind of important when you're interpreting your experimental data. So firstly, the calcium oxide sheet of the main layer seems extremely well ordered, okay? The smallest silicate chain unit is the Q1 dimer. It's nothing smaller. Experimentally in synthetic CSH, we never see Q0s. So Q0s, Q3s, and Q4s are incompatible with the CSH structure. So Q0s, because we don't see them, because then one of the Q silicates of the Q1 dimer will be missing. Q3, like I said, stacking disorder prohibits it. And Q4s are, I don't even know how you could put it in, because it's just the structure that prohibits it. Then the second is the ratio between the bridging sites and pairing sites of silicates must be 1:2. And that's kind of an easy check if your CSH is actually CSH, because a lot of times you can see in the literature NMR data where the ratio is not 2, which suggests a different material next to CSH. And the proportion of Q2B silicates must be smaller than 1/3. So 1/3 it is if you have a proper Tauber-Morais structure where all the Q2B silicates are present, but otherwise it needs to be less. So in cement, you know, we usually, if you're trying to characterize CSH, everybody uses the mean chain length to describe how defective the silicate chains are. So basically, a mean chain length of infinite means that you have all bridging sites populated by silicate. And then as the mean chain length decreases, the less and less bridging sites are present, the more defects are there, so more vacant they are. And that's a collection of data points that I found in the literature of CSH that reported calcium silicon ratio mean chain length, and we kind of see the trend that as the mean chain length is decreasing, the calcium silicon ratio of CSH is increasing. The thing is, that's the typical calculation of the mean chain length, so basically you kind of just look how many bridging sites you have and you calculate it, but if you understand the axioms, like in the next paper that we're going to publish soon, I have the whole derivation. You can just simplify the mean chain length to this equation, makes it kind of a lot easier to calculate it. But the problem with the mean chain length that I have is that the mean chain length is very not intuitive, and the mean chain length doesn't really tell you how much of the silicates are missing in the bridging sites. So for example, so I came up with a different metric, which I called occupation of bridging sites. So basically it literally tells you how many bridging sites are there. So for example, at a mean chain length of 3, you only have 25% of the bridging sites missing, which is kind of easier to interpret. Like, because if I tell you 25% of the sites, you're like, oh, okay, I get it, 25% of the sites are there. If I say a mean chain length of 3, who knows what it means? And you can see here on this graph that the problem with the mean chain length is that it doesn't scale linearly with the defectiveness of the silicate chains. So there's one thing. The other thing is when you plot it as basically from 0 to 1, how much bridging sites you have, the OBS, you can actually plot all of the data on the same plot. Your mean chain length doesn't go to 100, 200. So you can nicely plot everything next to itself. And what's one thing that you can see here, I grouped all the data points by the different synthesis methods of CSH. So we have double decomposition from the reaction of calcium oxide and silicon dioxide. And then we have here calcium hydroxide, SiO2, hydrating beta C2S, hydrating halide, and the direct precipitation, the method that we have. And you can kind of see that there are big differences when you plot it like this. Because like on the mean chain length, you really don't see it because they 3.1 and 3.2 look similar, but it's kind of different. And here I start assuming that maybe all synthesis methods don't produce the same CSH. And you need to be careful about it. I kind of group them by black and red. The black ones are the ones that you usually need like a month to produce because you mix the materials and you need to wait a month, so the kinetics are very slow. And the red ones are the ones which immediately happen, like direct precipitation. Once you add the calcium and you have supersaturation, you just precipitate CSH. So I really hope that's gonna be the new metric over the next years, because that one is really frustrating me and the atomistic community. So with understanding the axioms, you can define the lower bound of the calcium-silicon ratio that makes on CSH nanofoil still a nanofoil, okay? So basically, you have like two extreme cases. Now, if you imagine just a single main layer, they're not stacked, just one main layer. You have your calcium oxide sheet, and then you have the silicate chains. So either way, you have all of them present, you get a calcium-silicon ratio of 0.67, or all the bridging sites are vacant. You get a calcium-silicon ratio of 1. So that's a situation where you do not have yet any calcium adsorbed on the surface. So that makes you this line here. So the first thing which means this line is that anything that's below the line is not a nanofoil, because the axioms prohibit it. If it's above the line, it can be a nanofoil. Then it's just a question how many layers are stacked and how much calcium is incorporated. So first we see that nobody managed to make a CSH which will be a single nanofoil without any calcium adsorption. Second is, we have this point here, which should be a nanofoil. The reported, the Grangion paper from 2016, so the reported PXRD says that's a typical CSH nanofoil reflection, okay? But it's here. So it has a calcium silicate ratio of 0.57. It has a occupation of bridging sites of 0.94, for which the line says it can be low as 0.68 to still be a nanofoil. And then you kind of start wondering but PXRD says it is a nanofoil, but OBS says it's not a nanofoil. What is it? So if you look then at their Q3 speciation, you like kind of should get like a red light. Firstly, we said Q3 is not doable due to the random stacking. Like this suggests the layers are randomly stacked, so there should not be any Q3s. Plus, Q3s, if they would exist, they're basically Q2 sites, so their proportion should not be higher than 1/3, which says the axiom number 5. And they have 40%. So to me, this suggests that, okay, they have CSH, but they also have a secondary phase. And it's kind of a nice check if you're working at the lower calcium-silicon ratios to figure out, do you only have nanofoils, or do you also have the second phases? So yeah, so then it's the stacking with the interlayer. That one's kind of a little bit complicated. So usually we say that the calcium-silicon ratio, that the mean chain length or OBS is a function of the calcium-silicon ratio, but I kind of twisted it around, and I think that the calcium-silicon ratio is actually a function of the occupation of bridging sites, which is related to the pH. And I made like here I have like two simple models. One is I have a nanofoil where I only in the interlayer, I only have the calciums which are occupying the vacant bridging sites, okay? So that's this line here. So that means, again, that if you're on the line, that means the CSH data point is what I'm predicting the interlayer structure is. If it's above the line, that means we need to incorporate more calcium, either in the interlayer or on the surface. But if it's under the line, then it means it's not a stacked nanofoil, okay? So if you look at all those data points here, which are double decomposition, they kind of fall on the line between monolayer and a stacked nanofoil. So it seems that all those CSHs here are actually single nanofoils. Just one main layer, no stacking. And there's a paper from Wu et al. In small, where they show that you can really control the specific surface area by how fast you titrate, and they managed to get like specific surface areas of 500, which suggests actually a single monolayer. So then the other interlayer model, which is here, kind of assumes, okay, we have additional incorporation of calcium in the interlayer, and we only add one calcium per each Q1 dimer. So basically as the mean chain length is decreasing, or the OBS increasing, you have more and more of those Q1s, and for each Q1 we add additional calcium. So we get this line. So we see that the CSH made from calcium oxide and SiO2 kind of nicely fits the model 0 line, very heavily depleted interlayers, whereby this one with a little bit more richer interlayers starts better agreeing with the red dots. Okay? So that kind of suggests to me again that different synthesis methods probably have different calcium specking in the interlayer. But that brings me, like, like for the last 3 papers, I'm just ranting in my publications about calcium complexation on the surface. And here's the origin of it. Like we did another study with Hegoi Manzado, where we developed a new code to make CSH. And we were looking at different bulk structures. And basically what we see is that as soon as you increase your calcium in the interlayer above 1, so for each dimer, so each dimer present, you add 1 calcium. So that's like the maximum. You're already at layer spacing that are experimentally in generally not seen. Okay, so that's, I would say, that's the upper limit. But even if you have such a model of a interlayer, you see there's still data points of CSHs which are above the model line, suggesting, okay, even if you have the maximum possible packing of calcium in the interlayer, we still cannot go to calcium silicon ratios of 1:6, 1:7, 1:8. It's dependent on the OBS, but like we cannot reach those. So then was the question, what to do? I mean, where is the calcium? We don't know where the calcium is. So the idea is like, okay, then obviously the calcium must be on the surface. So we put all of the calcium on the surface. But the problem is that calcium ions have a very strong hydration shell. The surface, it's not strictly silicate, but it's half silicate, half calcium, because they're interchanged in the A direction. So you cannot immobilize so many calcium on the surface. So you need to co-adsorb, in theory, OH minuses with that, because otherwise you cannot fit so much calcium on the surface that you actually need. So then was the question, okay, how can we check if this is possible? So it's like, okay, we need to do some surface characterization. So we were with Paul, we went and talked to really good experts at EPFL and stuff. We wanted to do some harmonic spectroscopy. We were thinking to do solution AFM, but the problem is CSH looks like this. So either way, you need it as you need your particles as a perfect sphere, or you need to flatten them out and on a subtract to do those fancy characterizations. So we couldn't do it. So we were like, okay, then let's do zeta potentials. And zeta potential, as you know, is an indirect technique to investigate the structure of the electric double layer. So basically, somewhere far away from the particle, you measure a potential, which is a consequence of what's going on the surface in the solution conditions. So Maya, during her PhD, did a lot of experiments. So she was the one who synthesized CSH and showed me how to synthesize CSH. So she made different CSHs, different calcium silicon ratios, so different pHs. And what we saw is that as the calcium silicon ratio increases, so does the zeta potential in the supernatants. So we go from 6 millivolts to 40 millivolts, from 1.4 to 2.0 calcium silicon ratio. And then she took those, so those were as they are, and those she took out, washed with ethanol, and put them back into supernatant. So we see like a slight drop. So it seems that this complexation network, whatever is on surface, is very robust. It's very hard to wash it off. So then she also took it and was titrating the supernatants with HNO3, so the pH was lowering, so was also the zeta potential getting lower and lower. So it seems that this surface of CSH, the charge, is very solution dependent, very pH dependent. Higher pHs, higher charges, lower pHs, lower charges. But we still got all positive surface charges. And then she took the samples and filtered them and put them in sodium hydroxide pH 12 solution. And so supernatants are very rich in calcium, so sodium hydroxide was not. And we see a massive drop of the zeta potential to around 3 for calcium silicon ratio 1.75. So it suggested whatever is on the surface, okay, it does not get really, it gets removed by really lowering the pH, but it gets more removed if we also remove the calcium, okay? So I lately was like kind of wondering, because here we never checked the calcium silicon ratio of CSHs after changing solution conditions. So I went and synthesized CSH nanofoil, calcium silicon ratio 1.784, pH 12.82, so then we measured by ICP. It had a specific surface area of 118 by nitrogen adsorption. And then I repeated what Maya did. Basically, I washed it with ethanol, put it back to supernatant. I see a slight drop in calcium silicon ratio, which corresponds to the slight drop in the zeta potential. Then I again filtered it. I filtered the supernatant one and put it in sodium hydroxide pH 12. I see a massive drop to 1.52 calcium silicon ratio, which is basically the massive drop that we see in the zeta potential. So we're kind of, oh, okay, we're actually really removing a lot of calcium from the surface. I did remeasure the specific surface area just to make that no stacking and nothing occurred. And I will say that it's in the experimental error, so not much changed. The CSH was still the same number of layers, here probably around 5-ish, so no stacking. And that to me suggests there was also no calcium leaching, because if the specific surface area would increase, then I would assume that the calcium from the interlayers got out, but it didn't, so I assume all the calcium is inside. And there's like some nice studies on ion mobility in the CSH interlayers from Tullio Honorio, and also from ours, and from Goyal, where they see that CSH in the interlayers is very coordinated to the silicate chains and is highly immobile. So you cannot really put it out in 30-minute sonification. So this kind of suggests to me, okay, the calcium silicon ratio decrease we can solely attribute to what's going on in the surface. We didn't even change the CSH so far. But then, yeah, we were like we were doing modeling, so we were kind of wondering, yeah, but what's going atomistically there? So we used our models, like I showed them before. We made a nanofoil. We deprotonated 93% of the surface silanols, which makes heavily negatively charged surfaces. This is the approximated surface charge expected in calcium-rich solution at a pH of 13. And we added calcium, and also we needed anions. We added chloride to the simulation system, and we simulated. This is like a protocol developed by Milan Perdotta, with whom we collaborated on this, on how to retrieve zeta potentials from the simulations. So basically, you simulate the system under applied electric field. Your ions move, and as the ions move, they drag the water with them, and then from the water mobilities, you calculate the zeta potential. So we did that, and we saw that in our first case, where we have a surface that's deprotonated and only has calcium on it, nothing else, we get negative zeta potentials, but then we progressively were adding OH minus groups close to the surface, okay? And as we added OH minus groups to the surface, the zeta potentials got positive and kept increasing, okay? So we saw that from the simulations. And what's going on is basically that when you add an OH minus next to the surface, the OH minus can immobilize, coordinate up to 3 calciums at the same time. So like slight amount of OH minuses close to the surface, which at a pH of 12, 13 you have abundance, really help immobilizing calcium at the surface. Consequently, you increase the calcium silicon ratio and you start charge compensating the negative surface charge and turning it positive and keep increasing. So what's happening on the fundamental level is that if you imagine you have your surface, it's negatively charged, you don't really have many OH minuses, means that you start charge compensating the surface by the calcium which is close to the surface. Some does inner sphere adsorb, some stays mobile close to the surface. So you kind of overcompensate the surface charge, you get highly positive, the calcium is then dragging the water molecule in one direction, and that water movement of the water gives you negative zeta potentials. In the case where you have a lot of OH minuses, you basically, okay, you have negative surface charge, but then you have a highly positive surface charge due to the immobile adsorbed calcium on the surface, and because those are highly, you get a very positive surface charge layer on the negative charge, then your anions, OH minus or chlorides or whatever, move closer to the surface and they become the dominant ion that moves the water, but it moves it in the other direction, so it gives you positive zeta potentials. So that's kind of how we figured out, okay, there's really happening that OH minuses are key for surface complexation. So what happens at the end is that you create this, that's kind of long description, porous, non-ordered, water-holding, interconnected calcium 2+ and OH minus surface complexation network. So it's like they're connected by each other, there's a lot of water around, and everything seems very stable on the surface. And when you look at like such a three stack layer nanofoil with a calcium silicon ratio 1.3, where you have no calcium at that point on the surface, and you keep extending this calcium complexation network, you increase your calcium silicon ratio of the entire nanofoil. And for example, to go from here to here at 1.7, you can see that you need to adsorb around 7 calciums per nanometer square, which is a lot. You can only do it by creating these networks by OH minuses. And at the end, this ends in a 3-layer stack nanofoil, in a CSH nanofoil where 25% of all the calciums are on the surface. So the CSH, which forms 50% of ordinary Portland cement, the hardened cement paste, and if it has a calcium silicon ratio of 1.7, 1.8, you really have a big source of calcium on those surfaces that you can then freely use. So, but why co-adsorption? It makes maybe it makes sense, maybe it doesn't make sense. To us, it makes sense because to synthesize CSH, you're at high pHs. Generally, you need in our setup, if I don't have a pH of 12.7, I will get a globule. So I need a 12.7 to immediately precipitate a nanofoil. And at those pHs, your calcium speciation in the solution progressively shifts from Ca2+ to calcium CaOH complexes. So at pHs relevant to cement, at least initially, you have always abundance of those. So they seem kind of happy to just go on the surface at one point and be there. So with all of this, yeah, that's currently our latest nanofoil model. So that's like the 3-layer. I colored differently the different calciums. So here in the green, you have the main layer calciums. This I guess, violet, it's interlayer calciums, and in the blue you have the surface calciums, and that's our 1.77. And I need to say, for a very first quick try, it fits very excellent with the experimentally reported PDFs. All the peaks are there, further supporting the hypothesis that the main layers are highly ordered. There's a small difference here currently in the peak position, but this could be since we used empirical interatomic potentials. So by the computational limitations, I think today this is the best PDF of a CSH model that you can find, but it's not published yet. So to get to the end, to the last slide, knowing the CSH atomic level structure, like why it matters. Like I said, by really understanding the axioms, the structural axioms of the nanofoil, it can help you spot secondary phases. Because, like, I mean, if you have globules and nanofoils, it can be that the globules are masked behind the XRD pattern of the nanofoil, but then by calcium silicon ratio and silicon NMR, you can easily spot them. Like if there's a Q3, Q4, it's obviously not a nanofoil. It can help you get better insights into experimental observation. So especially with solid state nuclear magnetic resonance, we did a lot of papers on it. And by understanding the stacking of the nanofoils, lately they showed in the papers, you can really also help interpret the 1H NMR relaxometry, because the system seems dynamic from the amount of how the stacking goes and how the water migrates. And obviously it can help to correctly interpret phenomena at the CSH surface. So one thing I was like constantly wondering is actually carbonation, because usually you can read something like CSH under carbonation attack polymerizes, whereby the chains get interconnected by Q2 and Q3 silicates. So this doesn't make sense from what I see from the synthetic CSH, because firstly, like I said, like Q3 silicates, they're incompatible with the nanofoil. So as soon as you're starting getting Q3 silicates under carbonation attack, you're not having a nanofoil anymore. Q2s, you could technically have more Q2s, I will say, if you will keep growing your CSH longer at lower pHs, but when carbonation happens, you're quickly below a pH of 11, so you don't have conditions that you could precipitate CSH anymore. So it doesn't make sense that when you see the NMR and you have like, okay, you have a decrease in the Q1s, which are the CSH Q1s, and you have an increase in Q2, Q3, that's not a polymerization of CSH. So what I think is going on is if you have your CSH, you have a high calcium silicon ratio, you're at a pH of 13, it can be also cash. It doesn't really make such a big difference. And CO2 is penetrating your system, which is consequently lowering your pH. We showed in the zeta potential that the lowering the pH results in lowering the zeta potential, which means you're releasing calcium from the surface. And you're probably using calcium up to make calcium carbonate. And then as more CO2 is slowly going in, the lower the pH, okay, at one point you start then really dissolving the CSH. And as you're dissolving the CSH, you're also releasing the silicates, because here you still haven't released the silicates, but here you do now. And now those silicates and some calcium gets used for calcium carbonate, okay? And the remaining calcium and silicates that get used up at pH below 11, you make silica gel or maybe even the globule, depends on the solution condition. So I think that's much more realistic than the polymerization of CSH. But yeah, to experimentally in the complicated system quantify it, that can be a little bit tricky. So it's, yeah, I can help if anybody wants, but I'm not working in it, so I have my beautiful systems. So another thing where it kind of gets used to it, it was kind of fun study that we did with Franco Zunino, who's currently at Berkeley. He was applying for a grant and he was thinking if calcium NMR would make sense, if we could see anything for calcium NMR. the precondition is that you get money to buy the enriched calcium because it's quadrupolar and very big magnets. And I was like, oh, we're doing like all these DFT calculations. We're calculating silicate, NMR shiz, we can do zinc, alumina, like let's try calcium. So we did like some nanofoils and we calculated by density function theory the calcium, and we see there's a kind of simulated predicted calcium solid state NMR spectra of a CSH nanofoil. And we see from our structure that different calciums, like the main layer calcium, the bridging calcium, the pairing is like the interlayer calcium, and the surface calcium, they all should have like slightly different shifts. So it should be possible by calcium NMR to figure out the calcium distribution in CSH, which will be kind of cool if anybody gets the money in the machines. So yeah, and then we were like, okay, but what if we go to a little bit more complicated system? Could you track like the hydration reaction? Look how the calcium migrates from one phase to another. And our preliminary results show that like if you, there's a C3S hydration, which is in blue, and I have this peak, the orange one, which is CSH, and the red one is Portlandite, it should be very clear by calcium NMR to track how different phases form just by looking at this calcium, because calcium in all those phases, also calcium carbonate, has very distinct peaks. So back to carbonation, I think calcium NMR could really help figure out what's going on there. Yeah, I know. What's the Euro jackpot at this point? And the last thing, what I'm currently kind of obsessing about, and we look over the next summer mostly, is I call it chloride paradox, because chloride by itself, something doesn't make sense to me at least. So to my understanding, correct me if I'm wrong, chloride uptake in OPC cements is higher than, it's lower than in blended cements. So we have less chloride ingress in blended cements, which does not make sense if you think about what we learned about the CSH. So in OPC, we expect a CSH, there is CSH with a lot of calcium silicate ratio, a high calcium silicate ratio, which by what we are seeing should have a lot of calcium on the surface, which should be highly positive surfaces. But in like LC3 cements and all those, the calcium silicate ratio of cash is lower. So there should be less calcium on the surface, and the surface should be less positive, So, and chloride is minus, so chloride should prefer the high calcium silicate ratio CSH from OPC than from the blended cements, but the opposite happens. So the question is like, why? So my hypothesis that I write in my grant proposals are either there's some, so we know that the pore structure in blended cements are different. It's kind of more fine, if I remember correctly. So there's a beautiful paper from Milan Pradota with whom we did a zeta potential paper where they were looking at ion movement through nanopores of graphene. And the thing is, fun things start happening when you have overlap of electric double layers. So when they saw, if I remember correctly, an overlap of electric double layers, negative ions went into negatively charged nanopores. So that could be one thing, which is related to the pore size. Yeah. Or maybe there's something fundamentally interesting going on with the structure of the surface that we do not understand. Because in low calcium silicate ratio, you don't have so much calcium, so it's probably very easy for a chloride to get close to a calcium and make a pair and be uptaken. But if you have this network, which yes, indeed, is highly charged, so it attracts the calcium, but if the OH minuses, the OH groups are located at the top of the surface, it could be maybe kind of repelling for the chloride, preventing it from coordinating with calciums, plus a mechanism of chloride hopping that was documented on different materials could happen. Yeah, so it's a paradox in my opinion, but it's kind of fun to think about it and solve it. So in conclusion, I would argue that today we have a really good understanding of the CSH nanofoil structure. Okay, So if I have a CSH, I characterize it, I can probably make an excellent nanofoil model, and we can do whatever we want with it. The globule, I'm not so sure if it is even a CSH. Okay, I think it's more an amorphous calcium silicate, aka silica gel or alumina silica gel if you have alumina next to it. CSH is much more well ordered than anybody thinks, and we have axioms for it. No, CSHs from different synthesis routes have different distribution of calcium. So that means in practice, that means that calcium silicon ratio 1.3 from direct precipitation is perhaps not the same as calcium silicon ratio 1.3 from the reaction of calcium oxide and SiO2. So you really need to be careful, and always when you do CSH, properly characterize it. We're talking about the thickness, about how defective it is, but I know it's impossible to always do it because NMR hours cost a lot and take a long of time. So that's another thing that we need a better thing. And hopefully with the last 3 slides, I kind of convince you that it's important to understand the CSH structure of futures, because they can really help the interpretation of experimental results in hydrated systems. So that's all from my side. I need to mention all the people that made this work, especially the first one. He got me enthusiastic about cement.
So thank you very much. Thank you very much, Giga. We have some fantastic. I think I learned. I mean, I am into it, but still I keep learning. And how important, you convinced me how important it is to really work on pure synthetic CSH. Okay, I knew it, but I am even more convinced. There's time for questions. If somebody have a question here. I'm sure you can.
So it's very interesting, lots of things. But the chlorine one is something that's always baffled me as well.
The chloride?
You know, because I think one of the things we always forget is water. Like, how much does chlorine, like water, compared to calcium, and how much does that then, like OH, with respect to, I mean, okay, you're making your diagrams,
yeah,
and it's very difficult to characterize.
Yes.
But I think the competition of the hydrated chlorine ion compared to the hydrated calcium ion, and then how does OH interfere with that? Yeah. I think that's where you need more thought on how and what does the chlorine do once it's there?
Yeah.
Where does the chlorine go? What does it do, you know?
With everything in cement, I take like chloride NMR. But yeah, Milan did some nice stuff when they looked at calcium chloride pairing in solution. Will be maybe interesting to do calcium OH plus and chloride pairing in the solution and see what the free energy is when you're trying to get those close. I mean, it's a little bit hard to do it on the surface because it's a mess, as you see. But if you do it only in the solution, because like you also never know how the pH affects. Because like, you know, whenever you try to look up something, nobody did anything with pH 10 or higher, so you kind of need to redo everything.
So here, when you are comparing the retention of uptake of chlorine of blended cements with respect to OPC, in blended cements you have other phases.
Yes.
That are contributing also to this uptake. So
yes,
is really only CSH the responsible, or we have?
You see, that's why I'm gonna make a synthetic CSH and look at it, because I don't know which phase, what else is taking it up and how much. Yeah. So I wanna have my hardened cement base only CSH that I know what it is, because then we can quantify it.
Yeah, and we can discriminate because really in blended cement there are some phases that are taking.
Welcome to my ambizione.
I have, and then I'm looking at Anna here because I have been thinking of your in the CSH that you cannot have Q3, okay, unit or nanofoil. I was thinking in our alkali activated cements where we have Q3. So we you know, this is different structure, but perhaps we have to rethink also about that. We have Q3 with aluminium. It's okay?
I will definitely, yeah, like it doesn't really make a difference if it's cash or CSH.
Yeah.
I mean, alumina just behaves as a Q2B. I would, how old is the cement paste?
How old?
How much aged?
It can be, you see it from the beginning.
Oh, okay, from the start?
Yeah.
Yeah, then it's not CSH. Yeah, because like if it will be like very long times, I will say, okay, maybe when the kinetics are very slow.
No, but perhaps it comes part from, because when you use a sodium silicate, you kind of start seeing, you're right, part of the sodium silicate as an activator and then it's moving. But, and there is mainly the activator. But it was, I know, it made me think a lot about what we had. So we can have to, yeah.
How?
Carbonation. When you observe the presence of the Q3 in your drill is because you have a more silica hair, because the carbonation or you lose calcium. In our material, we have Q3, Q4 because we have aluminium. The difference is that, is my opinion.
Why would alumina make Q3 and Q4s?
I think it's a separate phase.
I mean, like, if you go back to the globule, you have the Q3s and Q4s, and they form when you have a pH of less than 12. Like, actually, the globule forms, if I'm completely strict, here I had pH 12, but even at pH 12.6, you can get a globule. It's really like what's your local solution concentration and everything. So
it's not CSH. It's an amorphous calcium silicate which doesn't follow the dry Ketten rule.
Yeah.
So it's not, for me, it's not CSH. The globule.
Me neither.
Yeah, and I think that's what these people, and the problem is, how do you find that out? I've scribbled down TEM because it's the same for you, a carbonation problem, but you know, these are horrible real systems, yeah? It's really difficult to find out what you've got.
Yeah, but perhaps we can do something on that, okay?
I really think that Q3, Q4 is a separate phase. It's not CSH. It's a silica gel.
Okay, yeah, we can. Good. So, plenty of work to do and discussion. Any other question in the room? No? Okay, if that's not the case, I thank you, Giga. Thanks a lot again for coming,
the invitation again.
for spending the time, okay, and dedicated to teach us more about CSH. I'm going to advertise the next, the next seminar. It's going to be on the 28th, no, when it was, 1 second. 20th of April, yeah, we say that. It's going to be given for somebody in the room, who is Hamza, who you, lo voy a decir en español, por Dios. Hamza, que ganó, sabéis, el premio en las últimas jornadas de investigadores en el área de la construcción, y el profesor con el que trabaja, ¿verdad?, que es Ramchi Haku. Por supuesto, todo esto vinculado, bueno, pues todo el trabajo que están haciendo con Inés, ¿verdad? Y él va a hablar, va a ser también en inglés nuevamente, y el título es Transforming Mine Waste into Sustainable Construction Materials, a Circular Economy Approach to Resource and Governance. Y os espero aquí el día 28 a todos, aquí físicamente, online, y os agradezco. Y un aplauso más para Giga por venir aquí. Gracias y encantada.